Except it just wasn't it because I ended up like doing a bunch of wrong stuff at the top. Wow. So.
Woo! How about 1? Good choice. Okay, good. Good. So I need, I'm going to do one of them, and then I need 2 volunteers to do the other 2. Boaz, you got one of these? Boaz, can you do just half the board, not the whole board? Yeah, and then 23. Oh man. Okay, hold on. Let's bring it all back together now. Eli, can you close the door? Welcome back, everyone. How was your spring break? Good. Miserable? I like these 6-day breaks. I think we should have 2 of them, though.
Renovate, and so I had to move all my stuff.
Oh, we also have
renovations.
my house hanging.
All right. You guys are not saying anything intelligible, so we're just going to begin. Boaz is doing number 17. Can I get someone to do number 23?
Oh my god.
Good. Going to the cards then.
That's so aggressive.
Iris, you are doing number 23.
Yeah.
Okay.
Iris, do you need a backup? Your backup is Joseph.
What?
Yeah, you're backup, right?
No, I'm not.
Okay, wait, hold on, everyone. Whoa.
Everyone, breathe in.
I don't know what I'm doing.
Breathe out.
Oh wait, for 23.
Alright, that was like a really aggressive first 2 minutes of class.
Yes, it was.
So everyone just calm down. Good. Welcome back. Now we're going to go over some homework. Boaz is going to do number 17. I need a volunteer to do number 23. There were no volunteers, so I picked Iris. Iris is requesting a backup, and the backup is therefore Joseph. So Iris is going to go, and you're going to like double check that she's doing it all right. Meanwhile, I'm going to do number 1 from the package, which is the function x, ln x. Okay, good. So, this problem I think is quite hard. This first problem from the package, and good. The calculus part maybe is not that difficult, but this is also a good example of how we have to also care about like end behavior and stuff like that. So let's go. First thing, maybe let's just take, well, actually, first thing maybe to notice is that the domain of this function is 0 to infinity. Yeah? Because I can only take the natural log of positive numbers. So just right off the bat, this is number 1, page 1 from the application differentiation package. And what's happening with number 23? Iris? Did you do it? Did you do the problem? No. Joseph, can you just do number 23? Like show all the work and take all the rooms and do all the stuff. Okay. So here we go. The domain is everything from 0 to infinity. Perhaps we should just right off the bat try to answer these limits on the bottom of the page, which is what's up. What? So what is the limit as x goes to infinity of x ln x, which is a very relevant thing to know for curve sketching purposes? Yeah. Oh boy. Good. Let's start over. I would like to take the limit as x goes to infinity of x ln x. Somewhere between 70% and all of you did this problem. This is page 1, problem 1 of the applications of differentiation packet. In order to curve sketch this, we need to know the end behavior, which is why I asked you to compute these limits. There's a box on the bottom of the page that asks you to do it. Yuri, can you turn that camera around? It's like on, I think, right?
Yeah.
Yeah, good. So what is the limit as x goes to infinity of x ln x? Everybody.
Like big.
It definitely goes to infinity. Thank you. That was would have been the appropriate response a minute ago. X goes to infinity, and the natural log of something very, very large also goes to infinity, but much slower. And so we're multiplying two things which are growing arbitrarily large, so the product is also arbitrarily large. Woo! Okay, a much more difficult question is what is the limit as x goes to 0 plus of x ln x. This is so difficult that there's an entire thing you're going to learn next year about how to handle these kinds of problems like properly. Why is it so hard? Would someone like to articulate why this is so hard? Lillian?
X goes to 0 and ln x, so like when it gets smaller is really big. So it's like 0 times infinity and you never know what that's going to.
If you take the natural log of a very, very, very tiny number, that's going to negative infinity. But here, as x goes to 0 plus, this is a very tiny thing. So we're multiplying a very tiny thing by like a huge negative thing. And so it's like not clear at all what the answer should be. Does anyone have like a kind of a, and so we don't have like a, we don't yet know like a definitive way of settling this, but we can kind of just like reason it out by just like being smart and stuff. Yeah, Daphne.
Just let's hope not the way ln x goes more slowly.
You have to be a little bit careful. Yeah, ln x grows more slowly than x does, but then that also means that like near 0, it grows down negative faster than x does. Is that your conclusion? What do you think the answer is? Oh wait, I think she's actually right. Maybe I said that backwards. Yeah, I think it is 0. A good way maybe to see this is that is kind of what I meant. I just kind of said it weird. A good way to see this would be to maybe just try to plug some number in. Like what's a very, very small number that goes nicely into natural log? Some power of e.
1 over e.
Yeah, exactly. If you try to plug into this function, like e to the negative 100, for example, or maybe it's more chill to just write it as like 1 over e to the 100. Okay, that is of course like a very, very small number, yeah? But when I plug it into the function, what do I get? Well, I get 1 over e to the 100 times, what is the ln of 1 over e to the 100? Negative 100. And so this is negative 100 over e to the 100. And so this is definitely going to 0. Like no chance. This is Alright, I thought that was actually the hardest part of this problem. Otherwise, it goes pretty smoothly. Let's take the derivative now. It's the derivative of the first times the second plus the first times the derivative of the second. And so my derivative function is just ln x plus 1. And, well, okay, let's just keep going. Second derivative, the derivative of ln x is just 1 over x, and there we go. So actually this was pretty chill. Well, let's just make sign charts now. So let's see. First I'll make a sign chart for f because I think I can. So where does f change sign? Well, x changes sign at 0 and natural log changes sign when? At 1. So I'm going to put 0 here and 1 here, and I'll say that therefore the sign chart is plus minus plus. But of course, everything to the left of 0 is just nonsense in this case because the domain of this function is only from 0 to infinity. But it still helps me make the correct sign chart. Alright, so I know that this function is going to be, another way of saying it is x is always positive on the domain. So the only sign change is happening at x equals 1. Okay, how about the sign chart for f prime? Where does f prime change sign? That one's maybe not so obvious either. I guess when is natural log equal to, when is natural log equal negative 1? Be careful, e to the negative 1, right? Yeah, maybe you can either do that in your head or you can just sort of off to the side say, when does ln x plus 1 equal 0? Answer, whenever ln x is negative 1, and that is when x is e to the negative 1, or 1 over e. So there's going to be this 1 over e point, and when the natural log is, or when x is bigger than that, ln x will be greater than 1, and it will be positive over here, and sort of negative over here. I also will throw in 0 because it doesn't make any sense to let it. Is this making sense? Okay, running out of space a little bit. But f double prime, when does it change sign? Well, only at 0. And so this is positive. And so what I've just learned is that my function is decreasing on the interval from 0 to 1 over e, increasing on the interval from 1 over e to infinity, and concave up the entire while. And now, maybe now is a good time to just sort of kill everything to the left of 0, because it's not in the domain of the function. Alright, so putting it all together using that method that we learned, my sort of shape chart, here's 1 over e, and really that's it, right? My function is decreasing concave up on the interval from 0 to 1 over e, and increasing concave up on the interval from 1 over e to infinity, and that's, I think that's all I need to know to make a good graph of this. So here we go. Let's plug in some numbers. Well, we just learned that the limit as x goes to 0 plus is 0. So that's 0. Where do we cross? We cross at 1. There's going to be another point. My function is concave up the whole while. If I plug in 1 over e, I just get negative 1 over e, actually, yeah? So 1 over e is like a third or whatever, so here it is. That's 1 over e comma negative 1 over e. And my function is decreasing, so I have a relative min there, and then, ta-da. How we doing? Alright, good, so that was a curve sketching problem. Boaz, are you going to have space to make the graph?
Oh, no.
Do you need to steal a little bit of Joseph's space? Yeah. Steal it quick before he fills it up. Good. While they are finishing that, so how are we doing on curve sketching basically?
Oh my gosh.
Good. Woo. All right. Let's also go over on the day before the SAT day. We learned about the second derivative test. So I wanted to give at least a couple problems on it just to make sure that you had it under control. Someone was G-chatting me over the weekend, just being like, "Yo, Mr. Rose, why do I care about the second derivative test?" And mostly we don't care about it. It's not that important. It doesn't get used that often, but it sometimes does get used. So I thought we could just do two problems really quick, 42 and 44. Yeah. So 42, I think is actually a good example of when you might use the second derivative test. So it's 2 sine. Who's taking responsibility for the camera? Like someone?
Oh, sorry.
I mean, it doesn't have to be you, but it has to be someone. Here we have this function, 2 sine x plus cosine 2x. And the goal of this problem is to find all the extrema. Okay, so here we go. I'm going to take the derivative. And what happens when I take the derivative? Well, I get the derivative of sine is cosine. And the derivative of cosine 2x will be negative 2 sine 2x. I think I did that right? Yep, I did. Okay, great. Now, I want to find critical values. Well, the smoothest way to find critical values is to just set this equal to 0 and then solve. So let's just do that. And I think the best way to do that is to factor. So this is 2. So this is 2 cosine x minus 4 sine x cosine x. And if I factor out a 2 cosine x, then I get 1 minus 2 sine x. I think that's right. Yeah, okay, good. Alright, well now this is just pre-calc, which is solving this. And when is cosine x equal to 0? Well, at pi over 2 and 3 pi over 2. And when is 1 minus 2 sine x 0? And that happens when sine x is a half. Zoom, zoom. So that happens when x is pi over 6 and 11 pi over 6. Alright, now, if I did not have the second derivative test in my life, then, what's up? Yeah. I messed up. I wasn't really paying attention. Whew, okay, good. Pi over 6 and 5 pi over 6. Okay, so I have 4 critical values. Nod with me if you're like, I got the 4 critical values. What I do not yet, assuming I did all my pre-calc right, confidence level 70%. Should I double check?
No.
You are correct.
Thank you. Voice. Okay, now, if I didn't, like I was saying, if I did not have the second derivative test in my life, what would I have to do next?
Plug them in.
Answer, I would have to go through that somewhat tedious, doable, but it's quite time-consuming and difficult process of like figuring out when this is positive and negative by making a whole sign chart and everything. Katie, you cool? Okay, so I don't want to do that, let's just say. So if I don't want to do all that, alternatively, I could just use the second derivative test. Anyway, the problem says for you to do that, so we should do that. The second derivative test says, let me just take one more derivative, which is not in general much work, because this would be negative 2 sine x, and this would be minus 4 cosine 2x. Let me double check that. Don't jump, it's chain rule and stuff. Yeah, okay, good. So now I have a second derivative. So alternatively to making this terrible sign chart, I could just now mindlessly plug in to this second derivative formula my critical points. And for example, if I plug in pi over 2, what do I get? I get negative 2, and the cosine of pi is negative 1, so that's like plus 4, yeah? I think I did that right. Negative 1, so plus 4, so that's just 2, which is positive. So what is my conclusion about pi over 2, therefore? It means that there's a relative min at x equals pi over 2. The reason being that I now know a couple things. I know that at pi over 2, there's a horizontal tangent. This is the entire justification of the second derivative test, because pi over 2 is one of the values that makes the derivative 0. But I also know that the second derivative is positive, which means it's concave up. And if it's concave up, then tangent lines lie below the curve. So in particular, this horizontal tangent line lies below the curve. And therefore, there's a relative min at x equals pi over 2. So it's kind of up to you. I'm not sure whether this is more work or less work. But let's say I only wanted to know what was going on at pi over 2. It's probably faster to just take a quick derivative and plug in pi over 2 than it is to make an entire sign chart and figure out whether the sign is changing from positive to negative at pi over 2. Okay, so if you're shrugging and you're like, I'm not convinced, okay, I'm with you. But anyway, this is how one uses the second derivative test. Cool? Woo! Let's just do one more. Let's plug in pi over 6 and see what happens. If I plug pi over 6 in, then that's like a half. So that's negative 1. And that's cosine pi over 3 is also a half. So that's minus 2, so that's negative 3. Let me just double check that. Cosine pi over 2, 1 pi over 3, 1/2, negative 2. I'm pretty sure that's right. So therefore, that's negative. And therefore, I now learn via the second derivative test that there is a relative max at x equals pi over 6. The justification being that here at pi over 6, I know there is a horizontal tangent because pi over 6 is one of my critical values, which makes the derivative 0. But also, the second derivative is negative there, which means the function is concave down, which based on our definition of concave down, the tangent lines lie above the curve, so that tangent line lies above the curve, so the function lives below that tangent line, so there's a relative max. How do we do it on the second derivative test? Do we even need to go over another problem, or is that just sufficient? I think that's sufficient. Woo! All right. Number 17, done by the Boaz. What I like about this problem is that 80 to 90% of it is just pre-calc, actually. This is one of those functions that we graphed functions like this back in pre-calc C. So the only thing that we didn't know how to do, like let's just see about, hey, how much of this is just pre-calc. Well, one thing, let's see, did Boaz do it all? Boaz, did you ever like factor the numerator?
Yeah.
It doesn't factor? Note, Boaz notes that this, not only does it not, it doesn't factor, but also just straight up like the discriminant is negative, so this has no roots. So that's good to know. So that's good to know. And then what else do I know? Well, the sign changes at 4. So therefore, we can make a sign chart, which he kind of does right here. And so remember how back in Precalc C, what was the next thing we would have done in Precalc C? We would have done exactly what he does, which is to do polynomial long division, so you should have done this anyway. And we get that there is the slant asymptote of y equals x minus 2. So like almost all of this was just Precalc C, and then we would have just, using the sign chart, using the slant asymptote, knowing that there's a vertical asymptote at x equals 4, we would have just made the picture and everything would have been great. But the one thing we couldn't do back in Precalc C was to find the locations of the relative min and max. So that's basically the only new thing. And in order to do that, we have to do a bunch of work. So he takes the derivative, math happens, math happens, math happens, quotient rule, he gets it over here, it factors nicely. He takes the second derivative, quotient rule, quotient rule, quotient rule, things happen, and he also gets a nice expression. So then, he makes a sign chart for f prime, no sign change at 4, but there is a sign change at 2 and 6, so it's increasing, decreasing, increasing. Then he makes a sign chart for f double prime, which is changing sign only at 4. This is all good, and therefore it's concave down and then concave up. So the shape graph is like this, and basically the only exciting part of this is we learn that there is a relative max at x equals 2 and a relative min at x equals 6. Yo.
If the concavity changes on an asymptote, what is that called?
Yeah, there is sort of no unanimous agreement by math teachers on the precise definition of point of inflection. That is kind of a thing that I don't want to get drawn into that controversy. But if you send me an email, I will reply with a long blog post called "What is a point of inflection exactly?" It's not written by me, but I do have a math blog. Yeah, kind of.
Oh my god.
So who doesn't have a blog where they talk about math education? Good. Okay, he's searching for it. Good. So wait, Mark, to answer your question, no one would call that a point of inflection. We would just say the concavity changed at 4. But also, there's some more crazy cases where some people call it point of inflection, some people don't. So I just kind of avoid the controversy by just who cares?
Can we just call it asymptote of inflection?
If you would like to call it an asymptote of inflection, you may. And everyone will probably even know what you're talking about. Okay, good. Number 23. All right, handwriting's a little different, but I think we can figure this out. Let's go. This function is 3x to the 2/3 minus 2x. Let's see, the first thing that Joseph does is to factor out x to the 2/3. It's kind of an advanced move, but I think it's a good idea. And you're left with 3 minus 2 cube root x. This enables us to make a, where are all your sign charts? Or you just kind of,
I just combined them.
okay, good. By good I mean,
You're welcome. Try to read that.
by good I mean not so good. So then, yeah, all right, then he takes the derivative, which I think was the easy part, and then he takes the second derivative, which is also, I'm just gonna do this the proper way because I do think it's helpful. So what does the function look like? Well, he writes the function as negative x to the 2/3, 2 cube root x minus 3, which is I think a really good way of writing the function. And thus we see that there is a sign change in the function. When? At the cube of 3/2. So at 27/8. So that is a root, 27/8. And there'll be a sign change there. Note that x to the 2/3 is always positive, so it's the negative leading coefficient, however, is going to make it like a one of these type things. So the sign chart for this function is going to go negative positive. What about the sign chart for f prime? For f prime, let's see, he has 2x. Okay, maybe I'll do it over here. His derivative is 2x to the negative 1/3 minus 2. So I mean, depending on how you want to do this, you could just write this without negative.
Wait, is that backwards? Your F?
Is it? Oh, she is right. I did the wrong, I said the right thing with my hands, but I wrote the wrong thing on the words. Yep. So it's like plus 10. So yes, 2x to the negative 1 third minus 2. I guess the simplest thing to do would be to just kind of keep with our program of like factoring out the lowest power. So if you factor out 2x to the negative 1 third, you're going to live with 1 minus x to the 2 thirds, yeah? No. That was wrong. X to the 1 third. Because then if you multiply it back through, you get 2x to the negative 1 third minus 2x to the 0. Yeah. So what is this? This is really like 1 minus cube root x. And there's also a 2 up here. And then down here is cube root x. This to me is the most reasonable form to write the derivative in. Are you guys following this? A lot of like algebra here. That to me is a good form to write the derivative in because it shows what's going on. Well, first of all, it shows me one thing. It shows me that that this function's not differentiable at 0, and also why it's not differentiable at 0. What is happening to the derivative as x approaches 0? It's going up to like infinity, right? Because we're dividing by 0. And so I should expect a vertical tangent line at x equals 0. Who's with me? Because it's making the derivative like infinity. But there's a sign change at 0, and there's a sign change when this numerator changes, which is at 1. Okay, and then the actual sign chart is quite complicated, I guess, because maybe really, if we're being totally serious about this, maybe even I should factor out another negative. So like negative 2 cube root x minus 1 over cube root x. Maybe that's even more clear about what's happening at there, which is sign change at 0, sign change at 1, and it's like quadratic-y with negative leading coefficient. So everyone see the subtle difference there. Okay, so therefore my sign chart here is going to be, this is 0, this is 1, and it's going to be like this, negative, positive, negative. So, which is what he has as well, right? Yep. Okay, and then the second derivative, this is just, well, again, I think it's helpful to write out the second derivative in the most algebra-friendly form possible, which is negative 2 over 3x to the 4 thirds. And now you just have to know enough about x to the 4 thirds to know that it's always positive. Because if you raise something to an even numerator power, then it just like fries the negative. So therefore, this second derivative is just always negative, which tells me that this function is just always concave down. Okay, so putting it together, which I think we did all this correctly, it's just hard to read. Putting it together, the only numbers we care about are 0 and 1, and I had my function decreasing on the interval up to 0, increasing between 0 and 1, decreasing thereafter, and concave down the whole way. So here we are decreasing concave down, increasing concave down, and then finally decreasing concave down again. And that tells you everything you need to know. At x equals 0, there is a relative min, because the derivative goes from negative to positive. And in fact, it's going to be one of those like sharp, undifferentiable kind of relative mins. At x equals 1, there is a relative max. And if you wanted to even add one more extra kind of fact to this picture, we would note that like there's like a vertical tangent here. Okay. In this, maybe I don't need this dotted line. I don't know. Maybe some people like it. That this is more like coming in, very sharp. All right, cool. And actually, and then there's a root at 27/8, and it just goes down, down, down from there. So it's exactly what he said. And the last thing I'll say is that you kind of could have like expected this a little bit already, just from looking at the function, because what do we see is that this function is like locally bird at 0, right? And that's what this function really is. It's a negative bird times a kind of a cube rooty type thing. So there it is. Questions? How are we doing on curve sketching? All right. Eli, can you raise that board? Good. Let's go over something else, which is optimization. I assigned 2 optimization problems on the homework from the book and 4 from the packet. We probably have time to do like 2 of them. Both, can you erase that board also? Which 2 should we do?
We should do the like, we should do like 40.
49 maybe?
Yeah, we should do 49.
49?
49. It was like the boat thing.
Jeez, back in.
The one with the boat from the textbook? From the packet.
From the textbook.
That one was like a little harder, right?
Yeah, it had like the point B at like one
I did not know how to do
meter.
this is similar to 49.
Yeah.
Oh yeah, I did not like it.
Alright, let's go. This is good. This is an entire category of problem called minimum path problems. And the goal is to find the minimum timed path through like sort of different mediums. Okay, so, and there was a problem like this in the packet, and there was a problem like this in the textbook. The one from the packet I thought was like a little easier, but there's the same general gist. Okay, so a man is in a boat 2 miles from the nearest point on a coast. He is to go to a point Q, located 3 miles down the coast, and 1 mile inland. He can row at 2 miles per hour and walk at 4 miles per hour. Toward what point on the coast should he row in order to reach point Q in the least time? Alright, so it's like this. Here's the shoreline. Here is this person in a boat. This is 2 meters or miles off the shore. So this is like okay, and we're trying to get to a point which is 3 meters down the shore, but also 1 mile inland. Okay, so good. Now the question is, why not just what is typically, so this is like all water over here, and this is like land. Typically, what would be the shortest path to get you from the boat to the point Q? Straight line, yeah. And if you were indifferent as to rowing and walking, then yeah, you would just try to take the shortest distance between the 2 points. It's just a straight line, so of course. But now you can imagine that you really, really, really hate rowing. What if you hate rowing so much that every second spent rowing is just torture for you? Then what path might you take? You would just go straight there, right? And then to minimize the rowing, because the minimum amount of rowing occurs when you just row directly to the shore. And then you would probably just take the straight path from that point, yeah? Because then you're just walking. Good. What if you hate walking? Like you really, really hate walking. Like you broke your ankle, so your arms work fine, but your feet at every step is like pain. Then what would you do? Then you would row straight. Good. Okay, so do you see how like depending on what you care about, the shortest distance is not necessarily the best choice, yeah? I'm putting like no effort into this paperwork, so someone else